Hi guys, another little video in our practical electronics series, and this has to do with interfacing microcontrollers that run on 3.3 volts to 5 volts components and vice versa. Now, if you work with microcontrollers, you are probably aware that some of them run on 3.3 volts. Now, when Arduinos started, they were all 5 volts, and you didn't run into any problems if you wanted to interface those with standard TTL chips or 5 volts components. For instance, here we have a little relay, which we'll get to. It's a special one, it's a latching relay. It's a 5 volt one. You can tell because of the 5T, and that's most common. And this here is a M5 stamp-C3, which is an ESP32 based microcontroller. And similarly, I also use some of these TTGo ones. They got a little OLED display on them. Also ESP32. Then you got the STM32 controllers like this. They commonly referred to as a black pill. And here is another one, which some refer to as a blue pill. These are STM32 based components, microcontrollers. They all run on 3.3 volts, and they need 3.3 volts logic on the inputs, and they provide 3.3 logic on the outputs. And if you were to feed 5 volts on them, they are likely to get damaged, so you wouldn't want to do that. So how do you go about converting the voltages and so on? And the thing is that you can actually buy little boards, I believe I've seen, probably from places like Adafruit and so on, that actually do the voltage level conversions for you. However, it is so easy, depending on what you're building, to convert these voltages that I wouldn't buy one of those myself. But if you are that way inclined, if all you're doing is connecting modules together, that would probably work for you. In any case, what we have hooked up here is a 74LS07 chip, which is a suitable component for level conversion, which we'll look at the data sheet and go into that in more detail. I have two transistors connected to the output of this 3.3 output of this chip here, and they are connected with their collectors to 5 volts, and therefore they will be able to drive this relay here. So that's another way. This LED here is driven from the 5 volts via this 74LS07 chip. Okay, so this is probably a familiar component to many of you. 74LS07. It has hex or 6 buffers in them, from pin 1 to pin 2, 3 to pin 4, 5 to 6, 9 to 8, 11 to 10, 13 to 12. So looking at the datasheet, we can see that the internal output of this, but each one of these buffers is actually an open collector output. It's a transistor here where its collector is connected to the output pin. So if you look at the circuit internally to each one of these buffers, you will see that the output pin is connected to the collector of a transistor, and that's why it's called open collector outputs. And as is highlighted over here, you can see that the inputs can be driven from 2.5 volts or 3.3 or 5 volts, and this feature allows the use of this device as translators in a mixed system environment, which is exactly what we are talking about, which is what we're doing. We've got mixed 3.3 and 5 volt signals. Okay, so I have a digital multimeter here, and I've connected the display to the top right of the screen, so we're going to take some measurements. And right now, as you can see, the green LED is on. Now the way that this is connected is that we have is like this over here. We've got the 3.3 volts input from the microcontroller, goes to the LS07 buffer, which is an open collector output, of course. It's almost similar to what this transistor is looking like. This collector connected to load and then to plus 5 volts. So here we have the load connected to the output of the LS07, and we actually have it connected to 5 volts. And the load consists of an LED with a resistor in series with it. So that's what we actually have. If we push this button, now you can see we have 3.4 volts. Now what we're actually doing here is I've got this connected via a USB 3 socket plug, and the little microcontroller itself is actually outputting the 5 volts, and it is outputting the 3.3 volts onto this rail here, and it's actually giving us 3.4 volts. And the 5 volts is 5.04 volts. In any case, the input over here that we are actually providing right now to this thing is 3.4 volts, and the output is 3.1 volts. So in other words, the LED is not on because there is no insufficient voltage there. And when I push the button, now it is pulling it low, so it's actually sinking the current to the LED, and the output voltage is 4.2 volts. And I've got it running, of course, through this resistor here, so the diode wants, maybe 2 volts or something like that. So as you can see, the voltage is being translated by this chip quite effectively. So you can actually run loads up to 40 milliamps straight from this chip, according to the data sheet, because this thing wants a 3.3 volt input. But in actual fact, you could use one of these buffers in here and connect an input from a 5 volt device into it, and then connect the open collector output to the 3.3 volts, and you would be transferring the power back, as is like shown in this thing here. You can put 5 volts in. You'll need some sort of pull-up resistor, usually 10K, and then you'd have a 3.3 volts output. Conversely, if you got 3.3 volts coming in and you hook up a pull-up resistor to the plus 5 volts, then you'll be translating from 3.3 to 5 volts. Now there is also an LS06 chip, which is actually the same as this one, except it has an inverting output. And in some instances, depending on what other needs you have in your circuit, if you have the need for one or more inverting outputs, then you can actually use that chip, and then you can use two of those gates in series with each other to have the same effect as this one, as just as an option. Now the second way that we can do this is we can take the outputs from the microcontroller, and through some 10K resistors, like as shown over here, we can hook up a load. But what we actually have here is we got a relay here, which actually has two coils in it, and we'll look at that in a minute why that is. But each coil is connected to a transistor, so we got a 10K resistor on the 3.3 volt logic line on the controller, and we have just an ordinary little small signal transistor, which in our case is a BC548, but it could also be a 2N222, 2N3906, or whatever it is. Any of the common small signal transistors will work just as well, because we're actually using this transistor in, it's either completely off or it's completely on. And we've got the output connected through the relay coil, and we put a little diode across it for the when the relay is turned off, it'll produce a reverse voltage, and we want to dampen that with that diode here. And we got that connected to plus 5 volts, so we are controlling a 5 volt relay with 3.3 volts input. Okay, so, and we can actually see that happening. I've got this connected. See, now it is on, and now it is off. Now, this relay here is a latching relay. Some of you may not be aware that these things exist. I'm not sure. At one stage I wasn't. A normal relay is only on when there is current flowing through it. And if you have a battery operated circuit and you want to turn something on with a relay, now normally you would use a relay. This relay can handle up to 1 amp at 250 volts or something like that. And if you need to control something that is high voltage or higher current, then you can use a relay for that. But as I said, normal relays, the microcontroller would have to pull the turn the transistor on so that the relay can stay on, so it is continuously drawing some current. The actual resistance of the coil in here is 170 something ohms, so it might be drawing, I think, was it 29 milliamps or something. Obviously that would be a problem under certain circumstances. These ESP32 chips, for instance, can be put in deep sleep mode, where they only use very little current, and if you got to keep something on, you wouldn't want this thing to continue to draw current, so that wouldn't work. So that's where these latching relays come in. They just need a pulse on there. It's got a set and a reset coil, and it's more like a toggle switch. And once it is switched to a particular mode, it stays in that mode without drawing any current at all. In fact, you can even turn the microcontroller off and it would stay in that mode wherever it is switched to. So if we look at the data sheet, you can see how it has two coils. Between pin 1 and pin 5 is the set coil, and between pin 6 and 10 is the reset coil. Now, quite frankly, the set and reset is kind of a little bit arbitrary in a way, because it depends on which side of the it's like a double pole, double throw switch, and it depends on if you got it on the normally closed and normally open side, whether it really is a set or reset if you like. But in any case, it's got two coils. One coil will switch it one way, and the other coil will switch it the other way. Toggles one way or the other way. We actually have our LED connected to pin 4, so it is in that mode. So when I push the little button there, it actually switches from one coil to the other, and it'll toggle, as you saw. Okay, for the record, this is where I found the little latching relays. 5 pieces for $3.10 plus $3.37 shipping. That's $6.47 for 5, just for the record. So we got a pretty simple little program here. Let me move this output out of the way. Since it's very simple, I'm just using the Arduino IDE. For more complex applications, I tend to use Platform IO via Visual Studio Code, and in future when I do some projects, you'll probably see me using that. Okay, so we have a variable here called LED on, which is set to false by default, and we're defining some buttons over some pins over here. Pin 10 is going to be for the button, pin 7 is for set, pin 8 is for reset, pin LED is going to be 6, and as a setup we're just defining the pin modes for these outputs and input, and I am making sure over here that the pin is reset in the reset mode, so it's off for that relay. And I haven't really checked how small the pulse can be. I've got it set for 250 milliseconds. Seems to work. It might be able to work with less, but the way this little program here works is it's got a couple of delays there, which is actually this one over here is actually for debouncing the switch, because without that it's kind of switches back and forth rapidly a couple of times. Okay, so we have a little function here, toggle a relay, and an input, boolean input, set is true or false. If the set is true, then it'll say uses pin set. If it's false, it uses pin reset, and it does a digital write on the whatever pin it is, sets it to low, holds it there for a quarter of a second, and sets it to high afterwards. Because don't forget that in this, when you're using a circuit with a transistor with a load on the NPN transistor with a load on the collector, it actually inverts the signal, right? A high voltage on the base means that the transistor is on, and therefore the voltage is actually going to be low in our case. So it actually, and then in any case, it ends up inverting. So there is a total loop. It says, okay, is the button down? In other words, we got it connected to ground when the button is down, so it'd be low. If it is low, then toggle the LED on value to opposite to what it was. Then if it currently is on, then set the pin LED, which is the green LED that you should to high, otherwise it's offset to low, so it's toggling that LED off. And then we say toggle the relay according to that same value, and then delay another quarter second just to make sure that there is no bouncing going on. So that's as simple as that. Okay, so there's no point in hooking the multimeter up to the inputs and outputs here, because it's only a quarter of a second, and the multimeter takes more time than a quarter of a second to display its voltage. But as you can see, it is working just fine. The relay is latching on, off, on, off. So that's it. That is the various ways that you can interface with these microcontrollers that are 3.3 volts. And of course, there's more ways than this that you can do that. There you can hook up, instead of a normal transistor, you can hook up a JFET or a MOSFET or an IGBT if you're that way inclined. But this is by far the simplest way. Also, this transistor could be a Darlington transistor, and you can actually draw more current to it if you need it to be more sensitive, or it can be a power transistor. All sorts of options there depending on what you're trying to drive, but the principle will be the same. And if you're using MOSFETs or IGBTs, though, they usually need some special circuitry on the input because they have capacitance, very low, high impedance, but they got capacitance. And if you are, for some reason, got very fast signals going through them, that you would need to take care of that with some sort of driver or something. So an ordinary transistor is easier to deal with in these cases. Okay, so I thought this might be useful. These are the kind of things that I use when I develop circuits that have to be driven by microcontrollers, and I thought this would be a good thing to be a part of the practical electronics series. So if you like these kind of videos, let me know, especially by subscribing and clicking the little notify bell button and what have you, which would be helpful. And I will see you guys next time.